Determine the value of the limit of 1 over n squared as n tends to infinity, and use the epsilon n definition of the limit to actually prove this. So it's not that hard to see that as n tends to infinity, n squared is just going to become bigger and bigger and bigger. We're dividing 1 into more and more pieces, so each piece must be smaller. This is going to have a limit that's equal to 0. But now we actually have to prove that. So let's remember what's the epsilon n definition. Okay, for any epsilon greater than 0, there exists an n. So as long as we take values of n greater than capital N, okay, the value of the terms in our sequence minus 0, the limit that I'm suggesting, and the difference between these will be less than epsilon. So our goal is, for a given epsilon, find such an n that makes this work. And I find the best way to do this is to start with the conclusion, try and work backwards. Now, obviously, for the proper proof, we'll have to start with arbitrary epsilon, but let's just see what we can see playing around with this. We don't need to subtract 0, and when you realize that eventually n's positive, okay? Even if we started with lower indexes, eventually n is positive. So n squared is always non-negative, so we don't really need the absolute value bars here. Okay, and now n squared, epsilon, these things are both positive, so we can rearrange the inequality without changing the sign. Okay. And again, because we're working with a sequence here, we assume the n's are positive. We can just square root. And of course, epsilon is positive, so root epsilon exists. Okay. So this to me suggests that maybe n should be 1 over root epsilon. So let's make that the case. Okay, so here's our formal proof. Let epsilon greater than 0 be arbitrary. Okay, just some value. Doesn't matter what. So we propose n equal to 1 over root epsilon will satisfy the epsilon n definition. Okay. So what are we going to do? So suppose that little n is greater than this capital N, which I'll remind you is 1 over root epsilon. Okay, so since epsilon is positive, 1 over root epsilon, which is equal to n, is positive. So these n's here are positive. Okay. So squaring, I've made a mess of that word. So squaring both sides. Doesn't change the inequality. Whereas it might if we had negative numbers, or 1 positive and 1 negative. So n squared must be greater than 1 over epsilon. Okay. So furthermore, not furthermores. Furthermore, we can spell this out a little slower. Maybe we can rearrange like this. Now, since n is greater than 0, n squared greater than 0, so 1 over n squared. I just want to point out this is positive. So epsilon is greater than 1 over n squared, which is equal to 1 over n squared in absolute value. And we just add in the minus 0, and we point out that that's the conclusion we were looking for. Okay? We started with any epsilon, we proposed an n, and we just made this assumption, and our deductions led us to the desired conclusion. So yes, the limit exists. It is the 0 that we reasoned it was, but now we have a formal epsilon n proof.